Hello, I am Owen Lynch. I am a second-year master's student at Universiteit Utrecht in the Netherlands, and I'm being advised on my thesis by John Baez, and I am presenting here on joint work from me, John Baez, and Joe Moeller of NIST. And I'm going to get started because, yeah, a lot of material to cover. So the overview of this talk is that there are four main parts, and then we get in examples, and then I get to talk a little bit about philosophy in the conclusion. I don't get to talk about philosophy any other time, but I might. So in the first section, I'm going to ask, what is entropy? In the second section, I'm going to use what I've said about entropy to define what I call a thermostatic system. So the static and thermostatic refers to that I'm only thinking about equilibria. I'm not thinking about dynamics. The third section, I'm going to talk about how to compose these thermostatic systems with what I call the central dogma, which we'll get to. And then finally, I'll do parts 1 to 3 with operads. Okay. So what is entropy? So we can point to like a lot of different things that people call entropy. And it's kind of unclear whether this is a linguistic confusion or actually something real. But there's Shannon entropy, which we talked about a lot yet at the tutorial. There's thermodynamic entropy, which is like something that you measure. You measure heat flows, you measure temperature with, like a bomb calorimeter or something. And so it's like something that's actually in the world. Then there's von Neumann entropy, which is in the quantum case, which I understand that we're going to be hearing a lot about later today. And then there's Renyi entropy, which is a generalization of Shannon entropy. And these are all called entropy, but why? And I don't really know, but I do know why we use entropy a lot of the time. So a lot of the time, maximizing entropy subject to some constraint gives us the answer to a question that we care about. For instance, in Bayesian inference, the entropy maximization principle tells us what prior we should choose. Oh, one thing I should say about this talk, I'm going to give a lot of examples, and different examples might speak to you, different examples might not speak to you, depending on your background. If an example doesn't speak to you, don't worry about it, because there's going to be more. So another thing, reason why we care about entropy is when you maximize the equilibria, when you maximize entropy in the thermodynamical context, like what I was talking about before with the heat flows and temperature, it tells you where the equilibrium is, because of the second law. The second law says entropy always increases. When entropy can't increase anymore, you're stuck. That's the static point. And finally, in probability theory, there's this whole theory of large deviations, which I'm not going to get into, but is really fascinating. And entropy maximization also shows up there for telling you what kind of large deviation you're likely to see. And maybe all of these three are secretly the same, but I don't know. So I'm sort of, what is entropy? I don't know, but I do know a couple things about entropy that all of the different types of entropy that I know of seem to satisfy. So first of all, entropy is a function of states. You have a bunch of states, like maybe probability distributions, mixed states in a quantum system, or actual states of like a gas. And entropy is some function of that state. Second, mixing increases it. So intuitively, this is like if you have two boxes of gases with a divider and you remove the divider, the entropy goes up. That doesn't exactly correspond to the math, but well, that's sort of the intuition. It's related. The third thing is that entropy is additive over independent subsystems. So if I have some system over here and you have some system over here, and we think of them as the same system, then the entropy of the whole system, or when you think of this as like one system, should be the entropy of this system plus this system, as long as they're not interacting. And fourth, like I said before, it's something that we want to maximize subject to constraints, which answers various questions. Maybe it's the same question in disguise, but that's not clear. So we know the answer. It's like Hitchhiker's Guide. We know the answer to the universe. The answer to the universe is entropy maximization, but we don't know exactly what the question is. So these four things, that's all you need to know. That's all we're gonna do for this talk. And so just keep these things in mind as we go through this talk, because that should sort of help you keep things clear. Okay, so for part 2, we're going to formalize principles 1 and 2. So a thermostatic system consists of a convex space X and a concave function S. And up here is a little picture of concavity because it's hard to remember which functions are concave and which functions are convex. And concave is the one that goes like this. However, convex and concave, I haven't defined those exactly. That's what we're going to do this section. But as an example, a thermostatic system could be X is the set of probability distributions on 1 to n, and S is the Shannon entropy. Okay, so now let's talk about convexity and concavity. So a convex space is a set X along with a function C lambda from X times X to X for lambda in 0, 1, called the mixing operation. And the idea is that lambda sort of biases the mixing operation. We're going to mix X and Y, and when we have like a slider for how much X we want and how much Y we want. When that slider is at 1, we are fully X. So that's the first thing. If we're trying to mix two things, it doesn't matter where the slider is. We always just get X. Finally, this mixing is sort of symmetric. If we bias by lambda towards X, that's the same as biasing by 1 minus lambda towards Y. And finally, there's this associativity axiom, which is kind of confusing, and you just kind of have to work it out in examples. So for instance, but you don't have to. Don't get distracted and try to work out the associativity axiom. Just follow. So anyway, so an example is vector spaces are a convex space with the mixing operation given by this convex combination of lambda times X plus 1 minus lambda times Y. And so anyway, so this sort of abstract definition of a convex space has a long history, and it was originally sort of discovered or invented by Stone in 1949 and has been rediscovered many times. So let's talk about some more examples of convex spaces. So one big source of examples for convex spaces is convex subspaces of other convex spaces. So we said that a vector space is a convex space. So if you have a subset of a vector space that's closed under convex combinations, closed under the mixing operation, then that in itself is also a convex space. And so as an example, we have the simplex, which was talked about at the tutorial. I wish I used the nice notation delta sub n plus 1, which Ty uses. But anyways, so the simplex is basically the set of probability distributions on n plus 1 elements. And this is a subset of R n plus 1 that is closed under the convex combination, so it's convex. But there are also sort of more exotic convex spaces, so that are not normally what you think of when you think of convex spaces. So for instance, if A and what I call join is a semilattice, i.e. something that satisfies these axioms, then you can make A into a convex space with this mixing operation that anytime lambda is like not 0 or 1, anytime it's anything in the middle, we just take the join. So this is kind of like a discrete version of a convex space, because you could imagine A being actually finite. And the reason why we care about this generalized notion of convex space is because the extended reals are kind of a blend of these two things. So the extended reals have a convex structure where for normal finite reals, it's just the normal convex structure. But then we take plus infinity and we say, well, if you mix plus infinity with anything else, anything finite, you just get plus infinity. And then we say, when you mix negative infinity with anything else, including plus infinity, you get negative infinity. So this is, yeah?
I have a question. If I usually think of convex spaces as sitting inside of some sort of cone. If I took the cone associated with semilattice by tempering by positive reals or whatever, do you have an intuition for what that is?
No. Oh, he asked whether if you have a semilattice and you tensor it with the positive reals, which I don't even really know what that means. Okay. If that ends up being a convex space, and yeah, I don't know. I'm happy to talk about that later, but I gotta keep moving. So anyways, so yeah, negative infinity beats positive infinity. And we could have chosen this to be the other way around, but it turns out that this is the convention that makes sense. So, and why do we like the extended reals? Well, because the extended reals kind of have this fun property where for the normal reals, every non-empty subset that's bounded above has a least upper bound. But in the extended reals, every subset has a least upper bound. Because the supremum, the least upper bound of an unbounded subset, is positive infinity, and the supremum of an empty set is negative infinity. Okay, now this is a category theory talk, so I couldn't introduce a new thing like convex spaces without telling you what the morphisms are. So the sort of natural idea of a morphism between convex spaces is a convex linear function, which is a function from x to y that satisfies f of the mixture is equal to the mixture of the f's. But there's also other types of morphisms. So for instance, convex relations, just like relations generalize functions, convex relations generalize convex functions, and that's just a convex subspace of x times y. And the graph of a function is a convex relation only if and only if f is convex linear. So now we have a nice category, which is the category of convex spaces and convex linear functions. And then we have a nice category of convex spaces and convex relations, where the composition of relations is x is related to z if there exists a y such that x is related to y and y is related to z. Turns out this composition preserves the property of being convex. And finally, we also have sort of a slightly weaker notion of map. So a concave function, it's not quite convex linear, but the mixing still does something. And in this case, you need an order on the codomain. So R the extended reals has an ordering, and a concave function is S of the mix is greater than or equal to the mix of the S's. And this is exactly this property too, that mixing increases entropy. So that's why we assume that our entropy function is concave. And now let's give a couple examples of thermostatic systems. So here's an example. A gas has, so this is like thermodynamics, not probability, this is just plain old thermodynamics. A gas has the state space of R3, where the coordinates are the energy of the gas, the volume of the gas, and the number of particles in the gas. And in thermodynamics, because they're physicists, they're like, oh, there are lots of particles, so it's not a discrete number, it's a real number. So we do that too. And the interesting thing is that the entropy function, this is sort of known from physics, the entropy function is kind of all you need to describe the system, because the entropy function encodes in it the temperature of the system when you're at energy, volume, particle number. It encodes the pressure, and it encodes the chemical potential, which, if you don't know what chemical potential is, don't worry about it. It's kind of like an analogy to pressure. And so, oh, there's a sign problem. This should be negative p divided by t. Sorry about that. Okay. Anyways, so an ideal gas, you can or a non-ideal gas even, you can model it like this. As we said before, simplex along with Shannon entropy is also a thermostatic system. If you have the mixed states in a quantum system, which are the states on a Hilbert space, again, if you don't know what that is, don't worry about it, and you'll probably find out. You'll probably find out later today, and von Neumann entropy. But there are also like way simpler thermostatic systems that like I don't see talked about that much because they're kind of so simple that people overlook them. So one is just, well, okay, you have like a water tank, and the only thing that describes the water tank is the energy of the water tank. So we just have one, the state space is the positive reals, and we have one coordinate, which is u. And then the entropy is S of u equals C log u. And it turns out that if you take this equation 1 over t equals partial derivative of s with respect to u, then you end up with u equals ct, which is the equation that you would expect for a heat capacity. When you raise the temperature by 1 degree, then the heat goes up by c. And now if we think about like a very large heat tank with a very large capacity, then when you change the energy a little bit, the temperature doesn't really change. And if you sort of take the limit of this, what you get is a heat bath, which is you can take in or out any amount of energy, and the temperature stays the same. And the heat bath is modeled by S of u equals 1 over t times S of delta u equals 1 over t times delta u. The important thing is that this coordinate u is no longer the total energy of the system. The total energy of the system is infinite because it's like a big old heat bath. This is just the amount of energy that you've like taken in or out in a given situation. And this heat bath is like fundamental in thermodynamics and statistical mechanics. Like often you assume that there's a heat bath, but at least I haven't seen people sort of treat the heat bath as its own system. And that's kind of one of the reasons why I like this formalism, because the heat bath stands on its own footing here. Okay, so now we've defined what a thermostatic system is, and now we're moving into part 3, which is now we're going to learn how to compose them. So let's recall our 4 assumptions. So entropy is a function of states. Mixing increases it. It's additive over independent subsystems, and it's something that we want to maximize subject to constraints. We're going to use principles 3 and 4 to formalize composition. So, but before we leap into the general case, we're going to do a specific case. So we have 2 big tanks of water. Remember, a tank of water is just for the purposes of this presentation, it's just characterized by its internal energy, and they're connected by a conductor, so they can exchange energy between them. Now, as you remember, or you may not remember, the entropy of the tank of water is given by the heat capacity times log of the energy. And so now if we sort of just say, okay, now let's take these systems and look at them as one system. Well, what are the possible states? Well, you could have, each tank could have any energy, and the entropy of the whole system is just the sum of the entropy of the parts. And so this is like, we're just putting them together independently. And the second thing that we do is, okay, well, now let's assume that these tanks can exchange energy, but they can exchange energy only in such a way that the total energy is conserved. And so we model this with a convex relation, which says that the total energy U is related to the internal energies U1, U2, if and only if U1 plus U2 is equal to U. And we say that we assume that like energy passes back and forth between the two systems until the entropy is maximized. So and so we say that the entropy of like the state of total energy U is the supremum of all of like the states of the underlying system. Oh, you have a question?
Yeah, sorry, I'm not sure what you're doing on this slide. On the previous slide, you talked about taking the product of two thermostatic systems. What's happening on this slide? Are you defining the new thermostatic system?
Yeah, okay, so that was a good question. So he asked on the previous slide, I was defining the product of two thermostatic systems. Now I'm am I defining a new thermostatic system on this slide? The answer is yes, in a sense, yeah. So I'm making a new thermostatic system, which is built out of these individual systems. And the way I do it is I take their product, and then I look at how they can evolve with respect to a constraint. And then I say that, and then I parameterize it in terms of the conserved quantities of that evolution. So in this case, that conserved quantity is the total energy. And this definition of composition accords with your intuition about what it means to just like stick two systems and put them next to each other. Well, one thing that we would expect is that they end up being at the same temperature. And that is precisely implied by this formula, because at the supremum, it turns out that the partial derivative of S1 with respect to U1 is equal to the partial derivative of S2 with respect to U2. You can do out this math, and that proves that the temperature is the same. I mean, it proves in as much as you buy this model. And then moreover, you can actually compute this entropy. And it turns out that it's C1 plus C2 times log of U plus some constant K. But the point is that this new system just looks like a even bigger tank with heat capacity C1 plus C2, which is also pretty intuitive.
Sorry, one more thing.
Yeah.
So you had the product system, and then you constructed a new system just on X, which represents the total energy.
Yeah.
This slide describes a morphism from the first to the latter in terms of a relation.
So okay, so let me repeat the question. So the question was, I took a system, and I took two systems, and then I built this new system in terms of the conserved energy. Have I just described a morphism between these two systems? The answer is no. It's sort of the other way around. First I describe a morphism from the product from like x1 times x2 to x in terms of a convex relation. And then I bring the entropies on x1 and x2 forward into an entropy on x. And this is the central dogma of thermostatics. I've always wanted to call something a central dogma. And I made up the term I don't know if I made up the term thermostatics, but nobody else is using the term thermostatics, so I get to say what the central dogma is. And this is the central dogma. The central dogma is that composition is, first you do independent composition. So you take a bunch of thermostatic systems and you form their product and you sum their entropies. And then you take a relation between this big composed system and another space y, which we think of as our space of conserved quantities. And then we push forward the entropy on x to an entropy on y along this relation via this equation. So r lower star s of y, where y is in big Y, is the supremum over x and y in R of S of x. And now you can actually see why it was important that we can take the supremum of any set, because we want this to always be defined. And the set of x's such that x is related to y, that could be empty or could be unbounded. And in that case, the entropy is going to be negative infinity or infinity. Yeah, question?
So, what is this? Is it the form of R as a function? The graph function?
Yeah. Oh, is this, yes? Is this an interesting form if R is the graph of a function? Not particularly. Yeah. Okay. So this is the central dogma. And now we're going to talk about category theory. So I'm going to try to explain how we take this central dogma and implement it with an operatic algebra. I don't have time for this aside. Okay. So we're going to do everything with operads, just like Ginger Rogers said, I can do everything you can do with high heels, except instead of high heels, we're doing operads. So our raw materials. So this is also, if you were like, thermostatics, what is going on? All we need, this is sort of like a thin way, like a hourglass of for this talk. All you need to remember from the previous half is what is on this slide. So you have a category convrel, which has convex spaces as objects and convex relations as morphisms. Then there's a functor. Okay, this is not really remembering. This is actually new, but there's a functor from convrel to set, which takes a convex convex space and returns the set of entropy functions on that convex space. And then the action of this functor on relations is exactly what I said here. And then finally, we have a natural transformation, which sends entropy functions. It sends like a tuple of an entropy function on x1, on x2, blah, 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 to xn, to an entropy function on the product, which just sends this tuple to the sum of all of them. And note that when it's the empty product, you just get 0. Okay, and so basically out of these raw materials, we're going to sort of abstract and abstract and abstract until we get an operatic and an operatic algebra. So the first thing that we're going to do is we're going to make a symmetric monoidal category. So symmetric monoidal category consists of a category C along with a functor from C cross C to C, and an object I in C, such that it's sort of a generalization of a monad. So I'm not, or not a monad, a monoid. So I'm not going to get into this, but basically like this operation, which is normally called the monoidal product, but it looks like a tensor product, is sort of a weakly associative, weakly unital, weakly symmetric. or commutative. And as an example of this, any category with finite products or coproducts is a symmetric monoidal category, because you can say I have an object X and an object Y, and I'm just going to take their like product, and that's the tensor product here, or their coproduct. And so as an example of, category theory is the subject where the examples have examples. So as an example of a category with products, conv with functions has products given by the normal Cartesian product. And then conv-rel, because conv is a wide subcategory of conv-rel, which means that all of the objects in conv are in conv-rel, and all of the morphisms in conv are in conv-rel, but not vice versa. Then we can sort of extend that, we can put the symmetric monoidal structure on conv-rel. And so now we've made conv-rel into a symmetric monoidal category. Now, a lax symmetric monoidal functor from a symmetric monoidal category C to a symmetric monoidal category D is just, it's a normal functor from C to D, considered as categories, along with a natural transformation that goes from the product of f of the x's to f of the product of the x's. So you can think of this like in a group, for like a group homomorphism, this is like an equality. If this is like the group product, but for symmetric monoidal categories, we say we replace this equality by just a morphism. And why do we care about this? Well, because ent, this functor that sends a convex space to the set of concave functions on that space, is a lax symmetric monoidal functor along with ind, which is the independent product, which if we go back, we see that ind looks very much like this natural transformation. And it works. And so there are various equations that have to be satisfied. And if you're into equations and commutative diagrams, then you can read our paper. Okay, so now we sort of we've like repackaged this up a little bit into a conv-rel as a symmetric monoidal category, and then ent and ind as a lax symmetric monoidal functor. Now we're going to repackage it some more. So as Ted and I presented on Wednesday, an operad, so as Ted and I said, there are two types of operads. There's one type where all of the she called it a single colored versus multicolored operad. So we're only going to be thinking about multicolored operads, where there are a bunch of different, what I call types. And then for every like collection of like x1 to xn and y, so inputs and one output, there's a set of what I call operations that go from x1 to xn. And then there's like some suitably well-behaved composition. And given any symmetric monoidal category, we can build an operad out of it by saying that the operations that go from x1 to xn to y are just the morphisms that go from the monoidal product of all of the x1 to xn to the y. And so for instance, if we do this construction on conv-rel, we get types are convex sets and operations are convex relations from x1 to xn and y. And we can think of these convex relations as a description of how to compose, like a description of the conserved quantities for in x1, like in thermostatic systems with spaces x1 to xn. And now, okay, we're almost done, but a little bit more category theory. An operatic algebra consists of a set for every type and a function for every operation that sort of respects composition, identities, symmetries. And whenever you have a symmetric monoidal category and a lax symmetric monoidal functor, you can build an operad and an operad algebra out of this by saying, well, like you just assign the set to each type given by the functor, and then the action of the operations on elements of the operad algebra is given by, well, first you do the laxator. I guess I didn't say that word before, but that's what this is called for a lax symmetric monoidal functor. This map from f of x1 to f of, yeah, this map. And then you apply the action of the functor. And this construction that builds an operad algebra out of a lax symmetric monoidal functor, this is exactly the central dogma. First, you do independent composition, and then you take the supremum over constraints. And so when we apply this construction to Convrel and Ent, symmetric monoidal category Convrel, lax symmetric monoidal functor Ent, we get an operad algebra where the action of the operations in the operad algebra is the central dogma. Okay, we're done with all the category theory. Now we get to do a couple examples, which I have 5 minutes, so I'm not going to do the examples in very much detail. But so hopefully now you can sort of relax and kick back and see how this works in practice. So one example is, and this is an example that people in thermodynamics care about, and also in like chemistry, something that happens all the time. If you have a gas and then you hook up that gas to a heat bath, so maybe it's like a gas in some container, but that you can exchange heat through that container with the atmosphere, so the gas is kept at room temperature. And you can describe this by composing a gas in a heat bath by saying, okay, I'm going to fix the volume of the gas. Like the volume is conserved, the number of particles is conserved. You have like a rigid box, but the temperature is going to be determined by our heat bath because we can exchange heat. And so this, like, common scenario is modeled by this composition. Another example, and this is sort of a more exciting example, I think, is that when you're doing like chemistry, when you have like a bunch of reactions, there are conserved quantities in those reactions. So for instance, this is a reaction where an enzyme plus a substrate goes to an enzyme plus a product. And there are two conserved quantities in this reaction. First of all, the total amount of enzyme is conserved. And secondly, the total amount of substrate plus product is conserved.
What are those in your picture?
They're not in the picture.
Oh.
So, or not directly. So basically, this n vector is a vector of the quantities of enzyme substrate product. And then this picture says, okay, we have some gas, and we connect this gas to a pressure bath, which basically means like our container can expand or contract. So the reaction is happening at constant pressure. It's also attached to a heat bath, so it's happening at constant temperature. And then anything that happens has to conserve some quantities. So we say, okay, we fix the conserved quantities, and then we say, and then we can apply maximum entropy to figure out where our reaction is going to go. And this actually even can do like endothermic reactions where, you know, a reaction can release or take in heat, because that, yeah, anyways. Yeah.
There's a question in the chat.
Okay. Yeah.
So, David Spivak asked, what are the legal wiring diagrams here? Can I split U and bring it also out of the big circle? Can you repeat the question?
Yeah. The question is, what are the legal wiring diagrams here? So the answer is that for general convex spaces, wiring diagrams don't really make sense. But if we think about like the subcategory of convex spaces, which like essentially what we're doing here is we're looking at a subcategory where all of the objects are of the form the positive reals to the n, then you could think about something like that. So maybe like undirected wiring diagrams, or some sort of, you could put some sort of hypergraph structure, or bi-Frobenius algebra structure, I think, on that subcategory where you can like clone and add things. Does that answer the question? Okay. And finally, so this is sort of, yeah, another exciting model, and I'm not going to go into this in depth, but maybe if you've heard of the Ising model, then you can sort of, the state of the Ising model is like, the state space here is the probability distribution over lattice states, and then you can take like functions from those probability distributions, which are like the expected value of the magnetization or the expected value of the Hamiltonian, and then use those functions, you know, to make relations. So you could hook up an Ising model to a gas and have them equilibrate in temperature. And that's kind of exciting. Like, you know, we have these different things from different domains of entropy, and now they can talk to each other. And I haven't played with this as much as I want to, but you know, it's a little bit exciting to me. Okay, and now it's all over, and now I get to talk a little vaguely about stuff that I like. So first of all, one thing that I've sort of taken away from this whole experiment is that these 4 assumptions, we can do a lot with them. There's more to do that probably can't be done under these assumptions, but it was kind of fun to see how much you could get and how much you could model with just like, you know, convex space, concave function, independent composition is summing entropy, and then the answer to the question that we care about. We don't know what the question is, but the answer is maximizing entropy. And having different entropies in the same framing allows composition of previously incompatible systems. That was pretty cool. The central dogma, but the final takeaway that I want to give is that this central dogma of building an Operadic algebra from a lax-symmetric monadal functor, this generalizes beyond the thermostatic case. And I don't know if John Bay is in the audience, but he's not going to like this, but because I'm talking about future work, and he says never talk about future work. But in my thesis, I use a very similar thing to talk about dynamics. So this trick, which I did not come up with, I've seen it in a couple other places, including Sophie Libkin's paper on operatic modeling of physical systems. Maybe I'm forgetting the paper title, but in other places. But the point is, I didn't come up with it, but I think it's fun. And yeah, that's sort of the note I want to end on this. And if you are interested, you can read the paper. It's Compositional Thermostatics by John Baez, Owen Lynch, and Joe Moeller. You can, I'm not going to put the archive number. Nobody is going to like read the archive number from this slide. You can just Google it like a normal person. And thank you. And now I'm happy to answer any questions. Yes.
Can you do the same with their quantum probability with the density states and analyze the one-on-one?
Yes. Yeah. So that's, I gave this example. I didn't go into depth because most people, I assumed most people wouldn't know about this, but.
You might just roughly summarize.
Oh, yeah. Sorry. The question is, can you do this also with von Neumann entropy? And the answer is yes. So the set of mixed states of a quantum system, which I call STH, that's a convex space. You can take convex combinations of mixed states. And von Neumann entropy is a concave function from that convex space. So it fits in very nicely into this framework. So this actually allows you to compose quantum and classical systems. Quantum and quantum, yeah, sure. I mean, the question is, one question is like, okay, what relations between quantum systems can you express in this framework? And I don't know that exactly. I'm not really an expert on quantum or even a intermediate on quantum. So yeah, but I would love to hear the answer. Okay, cool.
So in particular, you didn't look at any examples like the ones that you were looking at for classical thermodynamic systems. Okay.
Yeah. No, I don't know that much about quantum mechanics. Yeah. Any more questions? Maybe from the audience?
Can you talk about dynamics? So you mentioned dynamics. I think you can say something about like the analog of the Boltzmann H theorem, right?
I don't know what the Boltzmann H theorem
Like
is.
Non-decreasing of entropy under certain mass, I guess.
Okay, yeah.
So and you have you can say categorical, right?
So I mentioned dynamics. The dynamics that I'm doing are sort of very different from this thermostatics. I'm more taking a differential geometry approach rather than like a convex systems approach / probability approach. So it's really like I'm really thinking about dynamics in terms of like very classical like steam engines, like before people even knew what particles were or whatever. Yeah. Yes.
You don't have to answer this, but so you have this functor from conrel, the set that takes all the possible entropy functions. Is this representable? I'm wondering if there's like a moduli state.
Is this okay? The question is this functor which takes an a convex space to the set of concave functions on that convex space, is that representable? Not that I know of. Like you're saying that a concave function should just be a relation with a certain space. I don't think so. I don't think so. I mean, I think that there's probably like, if you think about John Baez's convex, like categories internal to the category of convex spaces, then you can sort of formalize concave functions as sort of lax. So like, because the extended reals has a poset structure and that's sort of like a category internal to the category of convex spaces. So you could do like, sort of think about, yeah, internal categories to the category of convex spaces and then lax functors between those, and then and would be representable there. But that doesn't exactly, I don't know exactly how that meshes with relations. So
I think maybe then an easy way to see that there can be no representable functor just in this in the original setting is that it doesn't send colimits to limits. So it can't be representable, at least the way that we'd like.
Oh, fantastic. Thank you. Okay, any more questions? Yeah.
Is there like is there a chain rule for the von Neumann
entropy? The question was, is there an analog of the chain rule for von Neumann entropy or an analog of it? So one thing I've been thinking about recently is that, so I say that entropy is concave. So it's greater than the convex combination of the entropies of the states. And in the chain rule, we say exactly how much greater it is. Namely, it's greater than via the entropy of the convex combination that you're taking. And so this has sort of just been an idea that has been kicking around, but I was wondering, I'm interested to see if you could make a sort of more strict thing for, instead of concave functions, you could say functions that increase entropy exactly by this chain rule, or maybe less than this chain rule or something. I mean, it would rule out some of the systems that I'm considering, but then it might, you might be able to prove something interesting about it for other systems. Yeah, so that's a good question. All right, thank you so much. Thank you, John Torella, for inviting me to this. And I will pass it off to David Spivak.